Hello, good morning. In a series of videos, I will explain basics of reinforcement learning. So, reinforcement learning to begin with is learning without a teacher, but with a critic. We'll know what it means by and by. You may be knowing supervised learning. In supervised learning, there's a teacher. The teacher will tell what is the output, and the learner will try to mimic the teacher. But in supervised learning, there is no teacher, but you will have a critic, or you will get one reinforcement signal. We'll learn all those things. So, as a prelude, in reinforcement learning, we'll be trying to solve multi-stage decision making problems. And the solution will be to find a policy. That is, given a situation, what is your action? What is your decision? I'll give you one practical example which I have worked on. Is a power utility, say Kerala State Electricity Board. Kerala State Electricity Board has one, or all utilities have a major issue of generation scheduling. There are various complexities as far as generation scheduling is concerned. Let me simplify it. One of the scheduling problem is called unit commitment problem. I will try to explain it for non-electrical engineers also. Unit commitment problem is, say, in Kerala, no, we have Idiki, a big hydrothermal power plant. It can generate power, and there is a naphtha-based plant in Kayangulam, which also can generate power. Power generated from Idiki is very cheap, practically zero cost, maybe say 50 paisa. And power generated from Kayangulam is based on naphtha, say approximately 20 rupees per unit. And the power could be generated from many other diesel generation plants at various costs. Maybe one may be 3 rupees, another may be 5 rupees. We could buy power from the central grid based on the tariff available. Sometimes you'll get power as cheap as 1 rupee per unit. Sometimes it may go up to say 15 rupees per unit. It's a random variable. Sometimes you will get money back. The tariff may be negative. So the engineers sitting in load dispatch center has to decide how much power should be generated from Idiki, how much from naphtha, how much from diesel, how much power should we buy at every hour. So this is a complex decision making problem. Our engineers are capable of solving it using their experience, because we cannot say that since hydro is available, use hydro completely, it is cheap. If you use hydro completely today, March 24th, 3 months down the line, your Idiki dam will be, there will not be any water and we will have problem tomorrow. So the current decision will have future consequences. So we could solve this problem. Okay, this problem could be solved by making a lot of assumptions, and people have used various optimization techniques to solve these kinds of problems. Reinforcement learning is a good and powerful tool to solve decision making problem under uncertainty. If there is no uncertainty, there are other better methods. So with that prelude, let us start learning reinforcement learning. So in this video, I will be talking a very toy problem, a single stage decision making problem. As an example, now consider an n-arm bandit problem. There are n arms. This is a casino game where if you want to play an arm, you have to pay some money, say $10. You can go and play an arm. When you play an arm, it will give you a reward. When you play an arm, it will give you a reward. I'll call it as a reward. It will give you a reward. The problem with this endowment problem is the reward given by arm1 will not be always be same. It will be a random variable. That is, if I play arm1, I may get 11 rupees when I play the first time. Second time I may get 5 rupees. Third time I may get 7 rupees. Fourth time I may get 9 rupees. And when I play arm 2, first time I may get 6 rupees. Second time I may get 20 rupees. Third time I may get 15 rupees. So it's a random variable, okay. So we have to find the best arm on an expected sense. So in simple words, we want to find an arm which will give maximum reward on an average, so that later on the player could play the best arm. For this, one direct method is you play each arm n times. It's called, you can find sample mean. You play arm 1 10 times, then you can get the average. I'm calling the return you are getting as observation. So you play arm 1, the first time O1A, second time you play arm 1, you will get O2A, third time you play arm 1, you will get O3A, fourth time you play arm, you will get O4A. Like that, you will get O10A. You got 10 rewards. You divide by 10, you will get the quality of arm 1. How good is this is called action value. How good arm 1 is. Similarly, you can play for arm 2, then you can play arm 3, then you can play arm 4. Play all the, suppose you have 10 arms, play all the 10 arms. So you find QNA for all arms. Find the best arm or the greedy arm based on these estimates. So these are called estimates. This is not the expected value. The expected value is we don't know. So once we don't know the expected value, what you could do is you can estimate. You can make an approximation. What probability theory says is that this expression QNA is equal to sigma I equal to 1 to n OIA by n will tend to the expected value of Q of A. What we want is the expected value of Q of A. Expected value of Q of A is what we want. So you can get an estimate of the expected value by taking sample mean. So I'm assuming that you know basics of probability, like random variable, expected value, probability distribution, etc. in this course. So once you find the greedy arm, you are done. So the problem is to find which is the best arm. So this method has a lot of issues. One is what should be the value of n. Another one is suppose I know if I played few trials and the reward I'm getting from I played arm 1 and I'm getting almost every time I'm getting reward which is less than 10. Arm 2 always is giving me reward less than 50. Arm 3 is giving rewards around 20. Arm 4 is also giving rewards around 20. Then I can guess that arm 3 or 4 may be better. So there is no point in playing all the arms equal number of time. So let us go back to this experiment. I have simulated this, written the code, and so you can get the best arm from this equation. This expression is important, QNAG. If QNAG is max, all of you know maximum value, the index corresponding to the maximum value is called the argmax. That will be a gradient. I've written a code in MATLAB and how I played is I played arm 1. How many times I played arm 1? I played arm 1 5 times. Then first 5 episodes I played arm 1. Second, from 6th to 10th I played arm 2. Third to 4th I played arm 3. So on. So I played each arm 5 times. And this is observation. Can you tell which is the good arm, best arm? It is difficult. So what we want is we need to play all the arms equal number of times. If you are playing, you will not do this. What you will do is you will try to find the arm which is currently the best, currently the supposed to be best, and play more on that arm. So for that, there is and another issue of this method is, I suppose I had 10 observation, and based on 10 observation, I got the quality, the action value for arm 1. When I get the 11th observation, I have to again add up all these things, which is not an efficient way. Then when I get, and I have to store all these values. So can I get a recursive equation for this? So that is called Robin-Monroe algorithm. This algebra you could do. I would please let me know whether you know this algebra. What is the algebra? From this equation, Qna is sigma I equal to 1 to n oia by n. What is Qn plus 1a? It is sigma I equal to 1 to n plus 1 oia by n. So can I get Qn plus 1a from Qna and n plus 1th observation? It's possible. That is given by, and for finding expected value of any observation O of A, this equation could be done. What is the, you are getting some observation. That needn't be the outcome of the enablement problem. You are observing something. When you're observing something, you want to get the estimate of the expected value. So what you have to do is you have some guess for the expected value initially. If you don't know anything, assume it to be 0. Then you get the first observation. What does this equation says? Q1 of A is equal to Q0 of A plus alpha n into observation of A minus Q0 of A. And in the n plus 1th observation, when you get the n plus 1th observation, you have an estimate of Qn of A. Qn of A is the estimate of expected value of Q of A. I'll use simple terms. Qn plus 1A is the approximation for the average value of observation of A. So you have some estimate. Let that be Qn of A. You get a new observation. If that new observation is more than your estimate, you increase your estimate. If O of A is greater than Qn of A, Qn of A will increase. If O of A is less than Qn of A, this term will be negative, it will decrease. How much you decrease is decided by the step size. And if I choose alpha n is equal to 1 by n plus 1, that is a precise way of this. But Robin and Monroe has said that in their celebrated paper sometime in 1958, they have proved that this algorithm will converge to the true expected value if you choose alpha n which satisfies certain technical condition. One way for choosing alpha n is 1 by n. Alpha n equal to 1 by n will definitely converge. And for practical purpose, if you choose alpha n small value, say 0.01, this algorithm will converge. So there are various efficient way for solving the enablement problem instead of direct method. All learning algorithm has some form of Robin-Monroe algorithm, a strategy for balancing exploration versus exploitation. So initially we should explore. As we go further and further, we should exploit. What is exploitation? You play the arms which you think are good. What is exploration? You play random arm. I'll explain one such algorithm. Initialize action value estimate for each arm. Say you initialize every Q of A to be 0. Q1 is 0, Q2 is 0, Q3 is 0. Let us assume there are 5 arms. Q1 is 0, Q2 is 0, Q of 3 is 0, Q of 4 is 0, Q of 5 is 0. Then you will play, say, maximum episode. Let us say we'll take it as 100. Let us take it as 100. If you take it as 100, so episode is 1. So in the first episode, with probability epsilon, select random action. With probability of epsilon, select random action. That is, you have 5 arms. You take a random number between 1 and 5. So you got, say, 3. If it is 3, play that arm and observe the reward. So you have played the arm 3. You played arm 3 and you observe the reward. Once you get the reward, you will update what? You will update Q of 3. So first you will update Q of 3. You played arm 3, so you will update Q of 3. Then what we will go to episode 2. When episode 2 with probability epsilon, select random arm. So how will you do this with probability epsilon? You will generate a random number between 0 and 1. If the number is less than epsilon, you will play random action. If it is greater than epsilon, you will play the greedy action. So let us assume the random number is less than epsilon. So again we played a random. Say it was 2. Then what I'll play 2. I'll update the estimate for action 2. Like this, I'll play third time. My epsilon was, I generated a number, it was greater than epsilon. So what will I do? I play the greedy arm, the arm which is supposed to be better at the current point of time. Once you play like this, the algorithm will converge. And only thing is that there should be a mechanism for updating epsilon. Initially, the epsilon could be large, say 0.5. And as we proceed with the algorithm, the epsilon should be decreased gradually. So that the idea is you should have more exploration in the beginning, and as you proceed, the exploration should be reduced. So I have coded this and I'll show you the result. This is the actual mean. So we have 10 arms. Each arm is having a generator uniformly random number with different means. If you know the means, exact means, you know that arm number 6 is the best one. So what I did is I used this algorithm and found out QNFA. So QNFA is not very precise. What is should be realized is that it played, this is the frequency, the number of times each arm was played. You can see that arm 6 was played the maximum number of times, whereas arm 4 and arm 7, so it didn't play arm 1 too much. It knew that it is not good. So that's it. I have few questions. I'll type it here. You please give the answer in the comment box. So let me summarize one point. The algorithm should initially explore more, and as we proceed, it should exploit. So the question is, how should I decrease epsilon so that we can get a perfect balance of exploration versus exploitation? This is one question. Another question is, what is the problem if we explore more? Say epsilon is always constant, is always constant and always equal to zero point 0.6. Please give your answers in the comment box. Thank you.